Welcome back, everyone. This is part 3 in our little mini-series where we've completely torn apart our electrical system and are rebuilding it in order to show you how we've done it. In this video, I'll install our 750 watt MeanWell power supply that will act as our grid charger. Let's go inside and talk about that. So you might even ask, why have a grid charger? Thought you guys are fancy highfalutin solar powered YouTubers. And while it is true, we have a ton of solar, and in these tropical conditions with lots of sun, we have no problems powering our water heater, air conditioner, lights, freezers, everything without any problem. Even on overcast days, we have more than enough power to run the normal stuff. Fans, deep freeze, refrigerator, computers, lights, all that sort of stuff. Is no problem with our 1.5 kilowatts of solar on the roof. That's more than enough to make up our daily needs, even in the clouds. But sometimes we're parked under the trees in complete shade and we're making effectively no solar power, and then we're dependent on our batteries. Fortunately, we've got 11.5 kilowatts of battery storage, and so that's enough to last us 10 days, and generally we wouldn't stay there that long, so we run on our batteries and then move on. But there have been a handful of times when some grid charging would have been very helpful to have. For example, when we drove to Tuktoyaktuk at the Arctic Ocean in the far north of Canada, the sun never really rose. It just kind of skipped along the horizon, and once we got there and I saw they had their solar panels mounted on the side of the buildings, I knew I was in for trouble. To make matters worse, soon after we arrived at the Arctic, a big storm rolled in and we were socked in with heavy clouds, rain and snow for 10 days. This poor weather turned the road into soup, and a semi-truck carrying fuel jackknifed and slid down the hill and blocked the only road in or out. So we were kind of stuck there for 10 days, dependent completely on our batteries. We were parked right next to an outlet, but at that time we had no charger, no way to plug in, no way to charge. But we just squeaked by. On day 10 or 11, the storm passed and the sun came out and we started charging again. It felt a little bit like the Mars rover when the windstorm blows the dust off the solar panels. The second time we needed it was on the east coast of Guatemala. Dead of summer, it was hot, muggy, and overcast. After a few days of running our air conditioner, our batteries were on a slow decline. So while we don't always need it, when you need it, you really need it. It was at about this time we had a friend flying to the States, and so we asked him to pick us up the MeanWell RSP 750-15. And while it's not actually a charger by itself, it's a constant voltage, constant current power supply. It has no idea the state of charge of the battery or when it should stop charging. So it depends on the logic of the SBMS 0 to control when to turn on and off. I'll get back to that later. There's several big reasons why I chose this power supply over a big name grid charger. The first one I'll mention is the input voltage range. The datasheet shows input voltage range of 90 volts to 260 volts AC with the frequency of 47 to 63 hertz. What that means is you can plug into 220, 110, 50 hertz European voltages, wouldn't matter. It'll handle all that just fine. But the more important reason that's important is because having traveled through Central America, we've run into countless people with grid chargers that won't turn on. They have a lockout that they will throw a fault, little red LED fault, if the voltage is below 100 or over 130 volts, 129 volts. And that happens far more commonly than I would have guessed. I've personally measured voltages at outlets coming out between 85 and 145 volts. So having seen all that, that's one feather in the cap for this thing. I've tried it in plugs below 100 volts and up at 130, and it's happy as a clam, just puts out the power. The second problem with plugging into the grid down here is that the grid can be pretty weak. Many times we'll see homes or a property with a power box with a power meter and two breakers, two 10 amp breakers. And that's because electricity costs 4 to 5 times more in some of these countries than it does in Canada or the US. And because of that, most people don't use vast amounts of electricity. Certainly not high power loads like cooking, oven, that sort of thing. Furthermore, the wiring is often just run along a wall and stapled on, or strung through the trees, little sections of extension cord and black taped together. So the wiring is not up to spec where you'd want to put big loads on it. If I was to put a 2,000 watt oven, for example, on some of this wiring, it would most certainly be a fire hazard. This brings me to my point. This power supply has an adjustable current setting which is accessible via this connector. This allows us to turn down the power and charge a little bit slower, keeping the wires cool and everybody happy. This is also handy if you're running a small generator. For example, our 1000 watt Honda generator will stall out completely if I put this on at full load. So having the ability to turn down the power and run it at a lower wattage, a lower output, allows me to run it off of the generator, no problem. Another thing I really like about this power supply is it packs a big wallop in a small package. This thing will put out 60 amps all day long, and it's not much bigger than a softcover book. Another big thing for us was cost. For something we're not actually using all that much, we wouldn't want to be dropping $600 or $700 on a big blue charger. This one cost us $225, which is a third of those big bulky ones. So there's many other great features about this power supply, which I'll put on screen now. You can pause if you want to read that, but let's get to it. First we'll install the power cord. If you watched our last video, we scavenged this from our electric hot water heater. As you can see, I've terminated these wires with some eyelets. Safety third. Okay, let's power this thing on. As you can see, we're at 15 volts. There is a little voltage adjustment potentiometer here, but it's also adjustable via this connector. Some people's instinct would be to turn this down to 12 volts or whatever your battery voltage is, but because power will only flow from high to low, you need there to be a differential. So you need this output to be higher than the battery voltage, so we're going to leave this at 15 volts. This connection also has the option to set the maximum current, and so with this pre-installed jumper I get about 60 amps out of it, but we want to be able to dial that back for the reasons I've already mentioned. So I ordered a matching connector just so that I could solder on a switch and a potentiometer and keep the original intact. But because this is so small and all wired up in a confined space, I'll just show you how it's wired on a on-screen diagram. Basically, I've just got a 10K potentiometer, which is a variable resistor, and I've wired one end of the resistor to ground, the other end to the 5 volt reference, and the middle wiper pin to the current select pin, as shown on this diagram. So now when I turn the dial, it will limit the power between 10 amps and 60 amps, which I'll be able to demonstrate in just a moment once we get it all hooked up. Next is the power switch. This one's pretty simple. The original jumper connector just has the power always on, and it sends 12 volts from pin 14 to pin 13, and that signals power on. So just interrupting that wire will switch the power supply off. So this section is specifically for our longtime supporting channel member, Craig McKenzie. I saw some forums online, he was working through this same issue. It's a common belief that you can just inject 12 volts into pin 14 from an external source, and that will trigger the MeanWell power supply to power up. It would be perfect if that worked, but in my testing it didn't signal the power supply to turn on. It needs to be the 12 volts that's in pin 13 sent to pin 14 to trigger the MeanWell supply to turn on. Fortunately, it's easy to address that. You would just need an optocoupler connected between pin 13 and 14, and even more fortunately, the SBMS I has unused optocouplers in the external I/O ports. So we can just connect this directly to EXT-IO5 and have that trigger the power supply to turn on. I'm actually pretty happy I ran into that roadblock because it made me think about it, and that allows me to, as I said, connect the power switch to EXT-IO5, which allows me to set a lower than 100% state of charge. So, said differently, I'll be able to set this to, say, 80% and charge off the grid up to 80%, which will get us out of trouble, but not fully to 100, because I don't want my batteries fully at 100 all the time, just pegged off of redline. So this way I can set in the display on the SBMS I the set point that I want the charger to turn off at. So enough talky, let's go outside and let me show you where I'm going to install this and why. So around this side of the truck we have our storage area, and the lower section of this box is isolated from the rest of our living area. It's all made of aluminum, and it has a divider, insulated divider, which normally lives in here. Alright, so looking up into this compartment now, you can see there the two blue motors. That's our big ARB compressor. At the front part of this compartment is our air compressor, and then the yellow capped gray unit there is our 2000 watt pure sine wave inverter. And this power supply I have mounted up in here, out of the way, can't get stuff dropped on it if it's on the ceiling. So this mounts up in here, and a few reasons I've done that. The biggest being the skin of this power supply is its heat sink, and it dissipates the heat through its skin, and so by bolting it up against this aluminum box, it can shed that heat out into the ambient air. And there's also some fans in there which help. So on one side I have a piece of angle already which I can mount to, but the other side I need to build a little bracket, so I've made this one out of some 1/8 inch aluminum angle. So that's the mounting brackets figured out. Next I'm going to hook up the power wires, the output connections. For the positive, I've got this length of 4 gauge cable run up to our breakers that will connect to the V positive terminal, and then for V negative, ground, rather than running a big long wire to some grounded aluminum, I've just made this little bracket out of a piece of angle aluminum, and that will just bolt on here and then bolt to the heavy aluminum box, and that will be my very short low resistance ground connection. So I'm going to hook all of these up, coating all of the connectors with Noalox antioxidant electrical compound to prevent any corrosion between any of these aluminum and dissimilar metalled connections. So now the other end of that positive power wire we'll bring up here to breaker number 3. And on the other side of the breaker I've got this other chunk of welding cable. Okay, next step is to connect the other end of that wire to the charge shunt. This is the shunt that monitors our incoming charges. These of course come from the solar panels through the DSSR20s, which I showed in that first video. So as you can maybe tell, these are switched off right now. There's no charge current coming through this connector, through this connection. So Now the wire coming from the breaker, I can just add it to the other means of charging, which are all measured through this shunt. So next we can install the cover, which I just 3D printed. Before any of you get too worried about how hot these shunts get, please remember that I overrated them significantly. This large load shunt is rated at 400 amps and the smaller charge shunt at 200 amps, which is more than double what they should normally see. And further, I've added this thermistor, silver colored cylinder here between the two shunts, and over the last few weeks of testing, it doesn't heat up hardly at all. So now you know that I can close this up and not have to worry about heat. I did consider mounting a cooling fan in this cover, but like I said, they don't get that hot. So I printed this up. I did have to make a little bit of an adjustment here just now. I heated this area and pushed it against this bolt just to get that to fit. I did measure for these bolts, but I assumed that this one was as high as this one, and it turns out it's slightly taller. So a little bit of an adjustment there, no big deal. Now that we have all this new equipment installed, when we go to put this panel which covers it back, this thermostat for our S-Bar diesel heater sits proud of the back of this panel. As you can see, it's almost an inch thick, and so I've had to whittle that out and we'll relocate it somewhere else, which leaves this big gaping hole. And so to cover that up and make it look more presentable, I've 3D printed a little fan grill grate, which I'll just put some dots of silicone behind that and put it there to cover up my boo-boo. Alright, as you can see here, I've got the SBMS 0 solar inputs disabled. So as you can see on this chart, there's been 0 solar production throughout the day, and I've done that so that I have something I can charge. So I've just plugged in the charger now. Maybe you can hear the fans. And now I'll switch it on. Whoops, need to turn on the breaker too. And turn on the breaker. Alright, as you can see, I switched it on there. It was at about 10 amps, and now I've turned it up to 16. Now if I reach in here and turn the knob up a little more, you can hear the fans spin up. Now it's putting out 30 amps. And if I crank it, $58.5 amps. But if you leave it like this, you'd have big problems, because the SBMS needs to be able to turn the power supply off. So to do that, I've actually found a piece of Cat 5 cable, and I've connected the green wires to EXT IO5, external output number 5, and as you can see, when we go into the, where is it here, automation, external I/O, there are external I/O 3, 4, 5, and 6. So with the external output 5 set as type 3, it will trigger that output until it hits 90% and then turn it off. So I'll change that to 80, and now it'll charge until 80% and then turn off if it was connected. So let's do that now. So now at the other end of the Cat 5 cable, you can see I have stripped off the green with white with the green tracer, goes to EXT IO5 negative, and the green wire goes to EXT IO5 positive. That goes to pin 14 on that connector, and the negative goes to pin 13. Hopefully you could hear the fans spool up. This should run until 80% and then switch off automatically. I just missed this by just a moment, but it just clicked over to 80% and the charger switched off automatically.
Later that same evening.
So, as you can see in this graph, charger came on, we turned it off and on there a little bit, and it's putting out almost 800 watts. And here it charged up from, what was it, 79 to 80%, and then it turned off automatically. And then I turned the set point up to 85% and fiddled with it there a little bit. And then it charged up to 85% and turned off again. Then I turned it to 90% and it turned on. Again, charged up to 90% and then turned off automatically. Finally to 95% state of charge on the set point. Came up, charged for a little better than half an hour maybe, and turned itself off again. So I'm now comfortable that the SBMS 0 is triggering that output to turn off and that it's all wired correctly. I'll probably have this set to 80% normally, and now that I trust it's working, we can go and finish up the wiring. So as you can see here, I removed the little toggle switch and I soldered on this crappy screw terminal I salvaged from somewhere and tied this up a little bit. Now that it's proven and tested, I'm going to tape this up and tie it up a little bit better. I considered automating this charge current selection knob, using a little Wemos with an op amp to boost the 3-volt signal to a 5.5 volt signal, or experiment with one of these digital potentiometer circuits. That way our automation system could adjust the current of the charger on the fly as it deemed necessary. But for now, this is good enough. Like I said, we hope to not charge from the grid that often, but when we need it, we really need it. So it's good to have it on standby, ready to go. All right, so that's going to wrap this one up. I do have some adjustments to make to my Python code to differentiate between grid charge and solar charge, but that can wait for another day. That'll probably be in part 4 of this video series, where I show how we graph all of this data to Grafana using Python and InfluxDB. So if that's something you're interested in, hit the bell down below to be notified when that video comes out. Huge thank you to our supporting channel members. It's these guys' support that lets me make these videos without pitching completely irrelevant VPNs, audiobooks, and kids' craft sets. Thank you to these guys. If you're interested in some behind-the-scenes footage and extra content, consider hitting the join button down below and see your name up here too. In any case, thanks so much for watching. We'll see you next time.